Welcome to Course 4, Module 3, Chapter 7, Adapting Factory Floors for Zero Waste Production. This chapter explains how manufacturing facilities can move from traditional waste management towards circular production ecosystems. The core message is that zero waste is not only about reducing scrap on the shop floor. It also means redesigning products, processes, resource flows, and partnerships so materials, water, energy, and byproducts remain useful for as long as possible. We will connect lean green methods, continuous improvement, industrial symbiosis, closed-loop water, and renewable energy integration. Throughout the presentation, keep in mind that zero waste production is a practical operating model. It depends on technology, management routines, and collaboration across firms, not on a single isolated sustainability initiative. Use this opening to frame the chapter as a systems challenge for modern manufacturing leaders. Today we begin with an introduction to zero waste manufacturing and the main enablers on the shop floor. Then we examine how Lean Six Sigma, Kaizen, and continuous improvement support circular economy objectives. The next section reframes lean waste from simple non-value activity into missed life cycle value. After that, we move beyond the individual factory and look at industrial symbiosis, by-product valorization, and the operational conditions that make eco-industrial parks work. The final sections focus on two critical resource systems: closed-loop water and renewable energy grids. We finish with a conclusion and a short learning check based on the chapter exercises. This section introduces zero waste manufacturing as a redesign challenge. The focus is keeping materials in circulation through product design, process design, shop floor routines, circular economy principles, lean green methods, and Industry 4.0 technologies. This slide reframes zero waste production as a factory floor and value chain redesign challenge. In the chapter, zero waste manufacturing aims to minimize material consumption, prevent waste generation, and maximize reuse, recycling, remanufacturing, and product redesign across the entire value chain. The shift is broader than sorting waste at the end of a line. It includes designing for disassembly, running waste audits, using smart collection systems, processing mixed waste at higher value, and building industrial symbiosis relationships. Industry 4.0 technologies such as sensors, digital twins, and cyber-physical systems help track waste and energy in real time. The important point is that zero waste becomes embedded in routine production decisions rather than remaining a separate environmental target. Emphasize that the same operating logic must extend from design through end-of-life recovery. The chapter identifies several enabling approaches that change what happens directly on the production line. Lean Green and 3R or 6R methods map value streams, remove non-value-adding work, and prioritize reduction, reuse, and recycling. Industry 4.0 brings IoT sensors, cyber-physical systems, and digital twins, allowing plants to monitor waste and energy continuously. Additive manufacturing supports on-demand production and can use scrap or electronic waste as feedstock. Non-destructive inspection prevents defects before they become physical scrap or rework. Together, these approaches show that zero waste production is not based on one tool. It is a combined managerial, digital, and technical redesign of daily shop floor operations. Present the table as a toolbox that combines process discipline with newer digital capabilities. Zero waste principles become real only when they are translated into daily routines. The source document highlights green lean tools such as the Green Performance Map and Green Kaizen. These methods encourage operators to move practices up the waste hierarchy. Instead of accepting disposal as the default, teams ask whether waste can be reduced, reused, recycled, or prevented through redesign. Conventional lean tools also remain important because they reduce lead times, remove inefficiencies, and lower physical waste. The difference is that environmental performance becomes part of the same continuous improvement conversation as productivity. In practice, operators are trained to see material losses, energy losses, and rework as improvement opportunities during normal production. This makes continuous improvement a practical bridge between environmental goals and daily productivity. This slide summarizes the transition as a progressive ecosystem-level journey. The chapter does not describe zero waste as a single target that can be reached by one project. First, plants redesign products and processes so waste is avoided at the source. Second, they digitize material and energy control through sensors, IoT systems, and digital twins. Third, they connect to external symbiosis networks when materials or byproducts cannot be used internally. Finally, they integrate shared infrastructure, closed-loop water, and renewable energy systems. This staged view is important because many barriers exist, including capital costs, technology limitations, cultural resistance, data gaps, and space constraints. Zero waste therefore requires sustained change over time. Use this slide to explain why implementation must be planned as a long-term transformation. The following section explains how Lean Six Sigma, Kaizen, and continuous improvement supports circular economy goals. Familiar routines become practical tools for reducing waste, closing resource loops, and embedding circular thinking into daily operations. Lean, Six Sigma, and Kaizen align naturally with circular economy objectives because they all challenge unnecessary loss. Lean focuses on removing non-value activities and improving flow. Six Sigma reduces variation, defects, and rework. Kaizen builds a culture of incremental problem solving. When these methods are connected to circular economy thinking, the target expands beyond speed and cost. Teams also ask how to reduce emissions, conserve resources, use recovered materials, and keep products or components in circulation. The chapter emphasizes hybrid approaches such as Green Lean and Green Lean Six Sigma. These frameworks bridge operational efficiency and ecological sustainability by using familiar improvement routines to deliver circular outcomes. The slide prepares the audience to connect operational discipline with broader sustainability outcomes. Two frameworks in the chapter show how operations and circularity can be connected systematically. The Sustainable Lean framework combines lean production, the circular economy, and Industry 4.0. It identifies reverse logistics, life cycle management, and resource and energy management as shared pillars for circular transition. Circular Lean Six Sigma 4.0, or CLSS 4.0, goes further by combining circular economy practices, Industry 4.0 technologies, and Lean Six Sigma into a unified continuous improvement strategy. These frameworks matter because they give managers an implementation logic. They identify drivers such as competitive advantage, but also barriers that must be managed. In other words, circularity becomes part of structured operational decision-making. Together, these models help translate strategic sustainability language into actionable shop floor programs. The chapter reports that integrated Green Lean Six Sigma programs can produce measurable efficiency gains. Empirical studies cited in the source document show reductions of 20 to 40% in overall resource use and 7 to 12% in energy and material costs. Another example connects 5S implementation with circular economy practices, resulting in a 45% reduction in water use and improved productivity. These figures are important because they show that circular improvement is not only a sustainability aspiration. It can create operational and financial benefits. However, the numbers should be understood as evidence from specific studies, not universal guarantees. The practical lesson is that structured improvement methods can make circular performance visible and measurable. Use the figures to show why managers should track both environmental and operational indicators. Green Kaizen is central because it changes operator behavior. In traditional waste management, operators may only separate waste after it appears. With Green Kaizen, they are encouraged to observe where waste is created, solve the cause, and standardize better routines. The Green Performance Map uses the waste hierarchy to help teams move from disposal toward reduction and reuse. The chapter also highlights 5S and standardized problem-solving routines, especially for small and medium-sized enterprises. These routines make circular economy thinking part of everyday work rather than an occasional sustainability campaign. The key message is cultural as well as technical. People closest to the process learn to identify circular opportunities directly on the shop floor. Emphasize that circular behavior grows through repeated routines, not through one-time instructions alone. Lean, waste, in a circular economy. Waste is no longer only non-value activity inside the factory. It becomes missed life cycle value when products, materials, or components fail to circulate through reuse, repair, remanufacturing, or recovery. This slide contrasts traditional lean waste with circular lean waste. In the traditional view, the focus is mainly on immediate operational inefficiencies, including inventory, overproduction, unnecessary motion, waiting time, scrap, and defects. In the circular view, waste also includes unclosed loops, excessive virgin material use, shortened product lifetimes, block-free use or repair, and end-of-life value loss. The chapter describes waste as a design failure of loops. If a resource flow is not slowed, narrowed, or closed, it becomes waste. This is a powerful reframing because it connects product design, supply chain decisions, and recovery systems with lean thinking. Circular lean therefore expands the improvement boundary beyond the factory floor. Use the comparison to show how circular thinking changes the boundaries of improvement work. The chapter proposes new waste categories that reinterpret lean through a circular lens. Process waste still includes scrap, defects, and excess energy, but it also includes failure to design products for disassembly, reuse, or remanufacturing. Supply chain waste still includes inventory and transport inefficiencies, but it also includes missing reverse logistics, take-back systems, or secondary market infrastructure. End-of-life waste becomes a distinct concern because landfilling and incineration are treated as preventable outcomes rather than unavoidable final stages. This categorization helps managers identify where value is lost. It also shows why recycling alone is not always enough, because prevention, reuse, repair, and life extension often preserve more value. This structure gives managers a practical checklist for finding hidden circularity losses across operations. Reverse logistics becomes a core lean concern when end-of-use products are seen as reservoirs of latent value. The chapter explains that products which are not recovered are effectively wasted value in the supply chain. Therefore, circular lean thinking makes collection, sorting, repair, remanufacturing, and reuse part of operational strategy rather than peripheral environmental activities. The source document also warns against focusing only on material recycling. Recycling can be useful, but it may lose higher embedded value from labor, energy, components, and product functionality. A stronger circular approach prioritizes prevention, direct reuse, repair, and life extension before recycling. This perspective links upstream design choices with downstream recovery performance. Use this slide to stress that recovery planning should begin during product and process design. Industrial symbiosis and byproduct valorization show how firms convert residual materials, energy, water, and utilities into valuable inputs through collaboration and viable business models. Industrial symbiosis converts residual flows into shared value by linking firms through exchanges of materials, energy, water, and utilities. The chapter describes many cases where companies reduce disposal costs, substitute virgin inputs, and create new revenue streams by using byproducts. The operating logic is that waste from factory A can become a resource for factory B, while shared utilities support both. This also supports legal compliance and environmental performance. The concept is especially relevant for heavy industry, construction, furniture, agri-food, and bioresidual sectors. The main takeaway is that byproducts do not automatically become resources. They need organized relationships, quality requirements, logistics, and economic incentives that make exchange attractive for all partners. The case evidence in the chapter shows concrete byproduct to product chains. A Brazilian manufacturing network involving steel, cement, power, metals, and refractory facilities exchanges about 300,000 tons per year of byproducts. These include coal ash, mill scale, electric arc furnace dust, zinc and lead sludge, steam, and refractory leftovers. The drivers include cost reduction, new revenue sources, and legal requirements. In the Dutch construction sector, recycled concrete aggregates can replace primary aggregates when demand, supply, and pricing conditions align. Another example from the Brazilian furniture sector shows value creation from wood and process residues. Across these cases, industrial symbiosis diverts material from disposal and turns it into economic input. Use these cases to show that symbiosis can work across very different industrial sectors. Economic models help determine when industrial symbiosis is profitable and resilient. The chapter highlights enterprise input-output models and agent-based models that compare avoided disposal costs and reduced virgin input costs with transaction and cooperation costs. These models identify win-win regions where collaboration benefits all partners. They also examine how gains should be shared when supply and demand are uncertain. Other models test disruptions, such as sudden cost increases or interruptions in material flows, so firms can design more resilient exchanges. Competition models add another layer by asking how market demand and green consumer segments affect profitability. The practical message is that symbiosis requires both physical exchange and careful economic decision support. This slide highlights why technical feasibility must be matched by a robust economic case. Operational success in eco-industrial parks. Co-location is not enough. Parks need governance, management, shared infrastructure, trust, information exchange, and continuous learning to make symbiosis operational. Eco-industrial parks depend on coordinated operational enablers. The chapter identifies strong and stable regulation, clear entry rules, dedicated park management, financial and technical support, and trust-building mechanisms as essential factors. Regulations and entry standards encourage energy savings, emission reductions, and eco-efficiency. Park management coordinates symbiotic exchanges, monitors performance, and engages stakeholders. Financial and technical support helps firms invest in cleaner production, shared infrastructure, and process upgrades. Trust building and information sharing create the social conditions required for inter-firm collaboration. The key point is that no single factor is sufficient. EIP performance emerges from the interaction of governance, infrastructure, finance, data transparency, and continuous learning among participating companies. Use this slide to emphasize that successful parks are managed systems, not accidental clusters. Park management turns simple co-location into resilient exchange. The chapter describes 6 recurring public actor roles: operator, organizer, financer, supporter, policymaker, and regulator. Different eco-industrial parks combine these roles in different ways, but successful cases have clear coordination capacity. Public actors can provide policies, subsidies, infrastructure support, and regulation. At the same time, evidence from international park assessments suggests that public-private or private management structures often correlate with stronger EIP performance than purely public management. This does not mean public actors are unimportant. Rather, it means operational capability, responsiveness, and stakeholder coordination matter greatly. A strong park management entity helps translate environmental goals into daily exchange routines and monitoring systems. This point helps distinguish helpful public support from the need for strong operating management. Closed-loop water in manufacturing. Facilities reduce freshwater intake and wastewater discharge by separating streams, treating water to the required quality, monitoring use, and managing energy and residual trade-offs. Closed-loop water design begins with separation, control, and treatment. The chapter emphasizes wastewater stream segregation as a foundational best practice. High chemical effluents should be separated from low-load rinses so treatment can be targeted and reuse potential increased. Open-circuit cooling and cleaning systems can be redesigned into closed or recirculating circuits with smaller tanks, loop controls, and suitable equipment substitutions. Digital monitoring strengthens these systems by using wireless telemetry and plug-and-lean kits to track water consumption at process level. Managers can then detect leaks, identify overuse, and find new optimization opportunities. In short, effective water circularity depends on architecture, quality control, and real-time operational data. This slide explains why good water reuse starts with understanding each process stream separately. Water circularity can deliver major gains, but it also creates trade-offs. The source document reports reductions of 45 to 64% in water use in some applications, along with lower freshwater intake, lower wastewater volumes, shorter cleaning cycles, improved productivity, and stronger water security. These benefits are especially important in agri-food, dairy, and semiconductor contexts. However, intensifying recycling produces concentrated residual streams that require advanced treatment. It can also increase energy demand because more in-plant treatment is needed. Regulatory fragmentation may restrict loop closure, and operators need training to manage new routines. The chapter therefore recommends metrics such as the Water Circularity Index to make performance and trade-offs visible. Use this balanced view to avoid presenting water reuse as a simple technical fix. Renewable grids and production facilities. Factories become active energy hubs when they combine on-site generation, storage, demand response, grid trading, and flexible production scheduling. Renewable integration is operationalized through microgrids and flexibility. The chapter describes factories, warehouses, and logistics parks that combine solar photovoltaics, wind, batteries, and grid connections. These systems can buy and sell electricity hourly, use time-of-use prices, and sometimes benefit from feed-in tariffs. Grid-tied electrical hubs may combine renewable generation, storage, and backup systems while respecting curtailment limits. In cold storage and logistics environments, renewable supply must be coordinated with inventory control and temperature management so product quality is protected. The core design elements are local sizing and siting of generation and storage, transactive or peer-to-peer energy markets, and demand response that shifts loads toward periods of renewable availability. Emphasize that renewable integration depends on aligning energy availability with operational demand. The economic integration of renewable grids combines procurement, trading, and sector coupling. The chapter explains that carbon-neutral factories must compare off-site power purchase agreements with on-site solar or wind. Power purchase agreements are often favored in low wind locations, while on-site solar becomes more competitive when installation costs fall below certain thresholds. Two-way energy trading can reduce utility costs and create revenue when excess power is sold back to the grid. Sector coupling adds further value when electricity supports hydrogen production, power to heat, or flexible storage. Case studies show that demand-side flexibility can substantially reduce decarbonization costs. The key lesson is that renewable integration depends on business models as much as technology. This slide shows that decarbonization can reduce risk and create new revenue opportunities. The conclusion brings the chapter together in around 4 messages. First, design choices set the options. Modularity, design for disassembly, and early life cycle assessment determine whether repair, reuse, remanufacturing, and recycling remain feasible. Second, material simplicity sets quality. Monomaterials and homogeneous streams reduce sorting costs, property loss, and uncertainty in closed-loop recovery. Third, integrated teams set execution. Reverse logistics, procurement, suppliers, operations, and human resource incentives must enter the design brief from the start. The final takeaway is that closed-loop systems are not recovered only at the end of life. They are designed, procured, operated, and improved as one connected system from the beginning. This closes the argument by linking design feasibility, material quality, organizational execution, system resilience, and long-term recovery performance. Thank you for your attention. Next, we continue with Module 3, Chapter 8.